Hi students, I am Sheeba from Emmanuel Arasar JJ College of Engineering. Today we are learn about the topic attenuation and scattering losses. First we can see the attenuation. Attenuation means it is the gradual reduction in the intensity, amplitude or power of a signal or beam as it passes through a medium. It occurs in physics, radiology, and telecommunications through absorption, scattering, or reflection. For networking and telecommunications, the signal attenuation happens when Wi-Fi, radio, or data passing through copper and fiber optic cables weakens over long distances due to resistance, absorption, or scattering. Sound or light waves lose energy as they move through air, water, or physical barriers, making sounds quieter or light dimmer. Medical imaging. X-rays and ultrasound beams lose intensity as they pass through different types of body tissues, which helps create contrast in images like CT scans. In physics and acoustics, sound or light waves lose energy as they move through air, water, or physical barriers, making sounds quieter or light dimmer. Medical imaging, X-rays and ultrasound beams lose intensity as they pass through different types of body tissues, which helps create contrast in images like CT scans. In biology and medicine, it refers to making a virus or bacteria less harmful or virulent, often to create vaccines. Material absorption loss in silica glass fibers. Material absorption loss in silica glass fibers is a mechanism where light power turns into heat inside the core. It happens due to the inherent properties of pure glass or outside impurities introduced during manufacturing, limiting how far and clearly light signals can travel. There are two types of absorption, intrinsic absorption and extrinsic absorption. First we can see the intrinsic absorption. Intrinsic absorption occurs in ultraviolet region, that is, electronic transitions absorb light at start wavelengths. Next one, infrared region. Molecule vibrations of silicon oxygen bonds absorb light at a longer wavelengths. Low loss window. A clear zone exists between UV and IR bonds, peaking in performance near 1550 nanometer. Next one is extrinsic absorption. The extrinsic absorption occurs first one impurities, that is transition metals like iron, chromium and copper absorb light energy. Next one, hydroxyl ions. Residual water or moisture creates major absorption peaks, notably near 1.39 micrometer. Next we can see the scattering losses. First we can see the linear scattering losses. Linear scattering losses, signal attenuations caused by elastic interactions between light and microscopic structural or compositional variations in the glass. These losses happen at all power levels and split into Rayleigh scattering. Rayleigh scattering means from molecular density fluctuations and Mie scattering from larger structural defects. First one, Rayleigh scattering. The Rayleigh scattering occurs tiny random changes in glass density and composition formed when Silica cools from high manufacturing temperatures. The effect of Rayleigh scattering is inhomogeneities are smaller than the light wavelength, scattering light in all directions. The rule of Rayleigh scattering law scales with 1 by lambda power 4, meaning shorter wavelengths suffer much higher attenuation. Next one is Mie scattering. The cause of Mie scattering is imperfections or non-cylindrical structures in the core cladding boundary comparable in size to the light wavelength. The effect of Mie scattering is scatters light heavily in the forward direction out of the core. The solution of Mie scattering minimized to very low levels via precise manufacturing control. Next one is non-linear scattering losses. The non-linear scattering losses in optical fibers are power-dependent attenuation processes that occur when high optical power densities transfer light energy to different frequencies or models. Unlike on linear scattering, these effects only become active when input power exceeds a specific threshold limit. Next is the core characteristics. First one was power dependence. Inactive at low power triggers sharply when optical density crosses a critical threshold. Second one, frequency shift. Optical power transfers to a new frequency, causing signal distortion and loss at the original wavelength. Third one, high power systems, mostly observed in long single mode fibers carrying high density laser light or wavelength division multiplexing signals. The main types of nonlinear scattering: stimulated Brownian scattering and stimulated Raman scattering. First, we can see the stimulated Brownian scattering. Interaction between light waves and acoustic phenomena within the fiber lattice. It is called stimulated Brownian scattering. Scatters light backward and has a very low threshold power. It is often a few milliwatts. Next one, stimulated Raman scattering. Stimulated Raman scattering is the interaction between light waves and high frequency optical phenomena, that is molecular vibrations. It can occur in both forward and backward directions, affecting a much broader range of frequencies than SPS, that is stimulated Brownian scattering. First, we can see this Rayleigh scattering. Rayleigh scattering is the scattering of light or other electromagnetic waves by particles much smaller than the wavelength of the light. Named after Lord Rayleigh, it causes shorter wavelengths to scatter much more intensely than longer wavelengths, that is blue to red, which explains why the daytime sky appears blue and sunsets look red. How it works? First one, particle size. The scattering particles must be smaller than roughly 1/10 of the wavelength of the incident light. Second one, wavelength dependence. The intensity of the scattered light is inversely proportional to the fourth power of the wavelength. Third one, dipole radiation. The accelerating electric field of the light wave forces charges within the small molecule to vibrate, turning the particle into a tiny radiating dipole that emits light in all directions. The common examples are first one, blue sky. Because blue and violet light scatter more efficiently across the atmosphere, the diffuse light coming from all directions makes the daytime sky look blue. Red sunsets. When the sun is low on the horizon, its light travels through a much thicker layer of the atmosphere. Most of the blue light scatters away before reaching our eyes, leaving behind the longer red and orange wavelengths. Next one, mice scattering. Mice scattering, it is the physical process where light or other electromagnetic waves bounce off spherical particles that are roughly the same size as the wavelength of the light. It happens with larger air particles like dust, smoke, and water drops in clouds or fog. Unlike tiny particle scattering, it scatters all light colors equally, making clouds and fog light look like white. The key facts are first one, particle size. The particle width is close to the light wave size, that is about 0.2 to 10 times the wavelength. Second one, color handling. It travels all colors of visible light almost equally, unlike Rayleigh scattering, which favors blue. Third one, direction. Most light scatters forward through, some reflects backward or sideways. Fourth one, common sights. White clouds and thick fog, the bright white halo of light seen around the sun on a hazy day. Car high beams bouncing back at you in heavy fog. Finally, we can conclude the section. So, thank you, students.